let us begin by recapping that the diagrammatics that we have developed so far for phi-cubed theory. The generating function, the connected generating function for the connected Prince function given by z of j, that has in it the diagrams are at linear order in j. One has these diagrams and so on, where the dot represents the factor of j whose position space-time location is integrated over, and therefore they are indistinguishable. And the second at the second order, one has this, and the third order and so on. If you calculate the Green's function Gn, which has n coordinates, space-time coordinates as its argument, then at n equal to 1, we have these diagrams and so on. Basically the same diagram as in z of j, except that the dot is now replaced by a fixed space-time point. For n-point function, there will be n crosses, the fixed points where the derivative of with respect to j has taken place. Those are the external points, the value of which appears arguments in the Green's function here. For n equal to 2, we have x1, x2, and so on. N equal to 3, the first diagram is the same, x1, x2, x3. Second diagram is also the same with dots replaced by crosses. But for the third and fourth diagram here, the indistinguishability, when the indistinguishability of the dots gets converted to distinguishable crosses, then there are topologically inequivalent diagrams from each of them, and there are 3 topologically inequivalent diagrams from each one of them that correspond to interchange in the taking topologically inequivalent ways of distributing these labels x1, x2, x3 over these three points, and those are given by these 3 diagrams for this one. I'm writing them. I'm changing this configuration and writing them in this way because I want to maintain the same locations for the labels x1, x2, x3. So these are x1, x2, x3. Here it's x1, x2, x3, x1, x2, x3, and that's why the diagram rotates. Similarly, for the last one, for this diagram, And so these are the diagrams and so on. Now we also studied the momentum space Green's function, which have in momenta as in the arguments, they are the external momenta p1 to pn, and these diagrams, momentum space diagram, are exactly same as the position space diagrams, except that the labels in position space, the labels are removed. Instead of the external points, the points are replaced by arrows incoming external momenta. Okay, so each point you remove the label of the x labels, because these are not fixed points, and replace them by an incoming external momentum. So external points get replaced by incoming external momentum. So therefore x in points in external points x1 to xn are replaced by n incoming or all outgoing external momentum p1 to pn. So we are taking the convention that where the external momentum are all incoming. So n equal to 1, one would have this. There's only one momentum p which is coming in, that one leg that it has, external leg it has. Then n equal to 2, it has two momenta, one coming in from this side and the other coming in from that side. But these two momenta p1 and p2 are not independent, because p1 plus p2 equal to 0 because of the overall momentum conservation, and therefore there is essentially one momentum which is going like this. So on. N equal to 3, we have exactly the same situation. P1, P2, P3. P1, P2, P3. So again, I'm keeping the names of the external lines, like from here it is P1, it is P2, and it is P3. Similarly, it is P1, P2, P3, P1, P2, and P3. That's why I'm rotating the diagram at exactly the same reason as I did in position space diagrams. In this case, we have and so on. Okay. Now, as promised in the previous lecture, we will do a few exercises where we draw a momentum space diagram and then apply the momentum space Feynman diagram rules that we spelled out in the last lecture. Apply the rules to evaluate the expression, mathematical expression for these diagrams. And this is the exercise we will do now for a couple of diagrams. So sample calculations. Let's consider first G tilde. So we'll consider G tilde for P1 to P4, and the specific diagram in that, which is given by this. P1, P2, P3, P4. And then the rule says, let me also write down the rules, essential points of the rules here. Label all lines by momenta maintaining momentum conservation at each vertex and the overall momentum conservation. Okay, then after leveling all these momenta, all those lines in terms of the momenta, then for each vertex write a factor of I times g. For each loop, perform the loop integral, that the loop integral over the loop momentum that is not fixed by this momentum conservation. For each propagator, write 1 over I delta tilde, and finally multiply by the overall factor, the symmetry factor, 2 pi 1 over s times 2 pi to the power d times the overall delta function for overall momenta conservation. So that's sum over I pi, where pi's are the external momenta. Okay, so that's those are the rules that we shall follow. So following this rule, let us look at this diagram. So first label all the lines. So this is P1 coming, incoming, P2 incoming. So this line, if you put the arrow that way, then it is P1 plus P2. So the labeling and the arrows should be consistent. So with the momentum conservation, if P1 and P2 both are incoming, then P1 plus P2 must be outgoing. Similarly, P3 plus P4 here outgoing from this vertex, we should be P3 plus P4. Then there's a loop momentum, and if you label the loop momentum by L for this line, then for this line will be P1 plus P2 plus L, because at this vertex P1 plus P2 is coming in, L is coming in, so P1 plus P2 plus L should go out this way. This way. Okay, so that's why it's P1 plus P2 plus L. Now you write down according to follow the Feynman rules, write down the expression. There are how many? 1, 2, 3, and 4 vertices. So I g to the power 4, and then write for an n point function, there will be n external momenta, and therefore there will be n propagators like this. So always you will have n propagator factor associated to this diagram. And then let's go to the internal lines. The first internal line is here, and corresponding to that we have 1 over delta tilde P1 plus P2, and corresponding to this one we will have 1 over I delta tilde P3 plus P4. Then loop integral. So there is a loop integral dl over 2 pi to the power d times, there are two propagators involved in this loop, this one and this one. So this is L, and this is P1 plus P2 plus L. So 1 over, so what we have is 1 over I delta tilde L times 1 over I delta tilde P1 plus P2 plus L. And finally, the symmetry factor, the overall factor, which is symmetry factor 1 over s, and s is here 2 because there is a twofold symmetry for the interchange of these two lines, yeah, in the loop. So, and then 2 pi to the power d delta overall momentum conservation. That's the mathematical expression. Let's do another example in G tilde 4. This is another diagram that I'm drawing now. Okay. Let's label the momenta. This is P1, P2, P3, and P4. Internal lines are, this one is P1 plus P2, this one is P3 plus P4. Now, since P1 plus P2 is same as P3 plus P4 with a sign reversed, at this from vertex, these two lines themselves complete the momentum conservation, and therefore the third momentum must be 0. So if this is K1 equal to, that should be 0, and that K1 should be same as this one, because if you put the momentum conservation as these two vertices, the total momentum that is coming into the loop should go out, the same amount should go out. So this is K2 equal to 0. Now, if you label this momentum by L1, then this is K1 plus L1, which is L1 because K1 is 0, and this is L2. Okay, now write the mathematical expressions. There are 1, 2, 3, 4, 5, 6 vertex factors. So I g to the power 6. And then let me introduce a new notation, P of P1, P2, P3, P4, where P of P, Q, L, and so on is nothing but the product of the corresponding propagators. So that takes care of the, so this is always going to be, so P of P1 to Pn is always going to be present in any n-point function, which is basically coming from the external legs. Then for the internal legs, we have 1 over I delta tilde P1 plus P2, 1 over I delta tilde P3 plus P4. Then for K1, 1 over I delta tilde 0, for K2, 1 over I delta tilde 0. And then the loop momenta integral dL1 over 2 pi to the power d, dL2 over 2 pi to the power d. For the loop 1, the first loop, there are two propagators involved, this one and this one, and both of them carry momentum L1 because K1 is 0. So 1 over I delta tilde L1, 1 over I delta tilde L1, and for the second loop it is 1 over I delta tilde L2. That's it. This is and then the overall factor, the symmetry factor in this case has twofold symmetries. One is the interchange between these two lines, and the other is the twisting of this loop. So that is 1 over 2 to the power 2, and then 2 pi to the power d overall momentum conservation. Okay, so that's the that's how it works. Momentum space Green's functions. Now notice one thing, that in this rule we are in this rule says that one should label all the lines by momenta by maintaining the momentum conservation. One could alternatively, what one could alternatively do is to write So of course the external momenta, there is no choice. The alternative rule that I'm suggesting will be same for the external momentum. You would label the external momenta by the names, but then for the internal momenta, one could assign arbitrary momentum for all internal lines and integrate over them. So in this rule, according to the present rule, you use the momentum conservation, fix the internal line momentum, and then label them, and then that will automatically show you that some momenta for each loop there is one momentum that is not fixed by these conditions, and one should integrate over that. Alternatively, one could label all internal momenta by arbitrary names and then integrate over all those momenta, and put for each vertex put the delta function, momentum conserving delta function. So that will eat up the integral, the integrated internal momenta, except for the ones that correspond to loops. So that is another way of writing down. That's useful for some analysis. We will do that in the next. We will follow that in the next part. Yeah.